Good morning. Hope you had a nice weekend. Are there any more submissions for the homework assignment here? All right. I got some nice questions over the weekend, so it was good to see everybody working on the assignment. Just as a reminder, I'm more than happy to reply to your emails over the weekend. It doesn't bother me one bit. I like fluid mechanics enough that actually your emails asking questions, it's kind of a nice thing. Because we only get to meet twice per week, and that's kind of a bummer, you know. So if you send me emails, it's sort of like it's giving me more fluid mechanics to enjoy. So don't be shy. Your next assignment is due on Sunday the 6th, and then your first exam of the semester is on Tuesday the 8th. When we get together next time in class, this Tuesday of this week, I'll give you some more details about the exam. I'll explain the format of the exam and so on, but we're taking that exam in class during our normal class time, just to help you schedule your time. All right, today we're talking about buoyancy. Sorry guys, lecture's begun, you can't come in late. Today we're talking about buoyancy, and I wanted to show you a picture of a gas station in West Virginia. This is where I'm from, back in the United States. Based on the picture, any ideas what we're looking at here? I've already told you it's a gas station, so what do you think? It could be a truck based on the size, but in this case it's not a truck. What's that? Excavation? No, this is an accident. You think it would be on purpose, so it's not something that's happened intentionally. First of all, what is this big black thing poking up out of the pavement? If this is a filling station, that's where the fuel is stored. All right? So what happened in this photo is that in West Virginia, the groundwater is very close to the surface. It's a very wet, rainy region, and so there's a lot of water underground filling the pores in the soil. And when that happens, when there's a lot of water in the soil, and if the weight of a fuel tank like this is too low, it can push the fuel tank up and push the soil out of the way that's covering the fuel tank, and it even has enough upward force to break the asphalt and concrete that's above it. So here's a few more pictures of it, and that's exactly what happened here, is that the fuel tank was empty, and it was a very wet day where the water table came upwards, and it just simply broke through the pavement. So this is an illustration of buoyancy that occurred even when we're talking about things other than pure liquids. Buoyancy is an important effect that can be something you have to consider in geotechnical engineering and in structural engineering. And so that's what we're talking about today, is buoyancy. And the key item with buoyancy is the amount of water that's displaced by an object and the weight of the object itself. So let's watch a video that illustrates buoyancy and how it's used in order to control submarines. Okay. So we're just looking into the ocean. The submarine comes up. Now let me ask you a question. Why did the submarine stop? How come it didn't keep going higher? Why is it floating that much right now? Why isn't it sitting a little bit higher in the water?
The weight is equal to the buoyancy.
Okay, the weight is equal to the buoyancy. Right, exactly. It's reached equilibrium at this point. That's why it's floating right now, is that it came into equilibrium. And so that's what we're going to be doing with buoyancy, is we're going to be considering force balances. So we're going to be looking at how does the forces acting on the object compare to the weight of the object. And so just to give you an idea of that simplification where we say that the buoyant force is equal to the volume of water displaced, that's a simplification, but let's look from the beginning at the basics of what's happening to an object that's submerged underwater. What you know from the hydrostatic equation, so the hydrostatic equation delta P is delta H times gamma, that for some fluid that has a unit weight of gamma, the higher the depth is, so with a big delta H, there's a big delta P. So you can see in this drawing, the arrows on the underside of the object are longer than the arrows on the top of the object. And so the interpretation of that is that the bottom of this, whatever it is, it doesn't really matter what it is, it's an irregularly shaped object. At the bottom, the pressure is pushing up larger than the pressure on the top is pushing down. And we've seen something similar to that before when we were looking at a submerged cube. And we were considering the pressure on the top compared to the pressure on the bottom. Or maybe that example's today. No, that example's today. I was working through it before the weekend, so that's why I think we've talked about it before. All right, so what we have to do is consider the difference in the pressure between the top and the bottom. And so that's why the pressure is higher on the bottom, is because on the bottom the delta H is bigger. And if we consider the volumes involved, we can find the volume of water above the object and label that V sub A. And V sub A is going to give us the weight of the water that's pushing downward. So here I've said force down is going to be the unit weight multiplied by the volume of water above the object. And the forces that are pushing up on the object are going to be equal to the volume of the body and the volume of liquid above the body. And so that's the net pressure that's acting upwards on that. And so if we consider the difference in the forces, the difference between the upward and downward forces, then F sub B, what we're calling the buoyant force, is just equal to the volume of the object itself multiplied by the unit weight. So what determines if it floats or sinks is when we compare the weight of the object to the buoyant forces of the object. And so let's take a look at that with this cube. This is a plastic cube, and it has a volume of 1 by 1 by 1. So it's easy for us to calculate the volume on this one. We say that it has negligible weight. Whatever plastic it's made out of is very, very light. And so the weight of this object is so low that we can neglect it. Let's say it's a hypothetical thing. And it's submerged 3 meters below the surface, and so the top surface is 3 meters below the water, and the bottom surface is 4 meters below the bottom of the water. And so just as a check, so that we can compare the buoyant force approach to the difference in pressures and the difference of forces, go through these steps of, first of all, calculating the force on the bottom, the force on the top, the difference between the two in part C, and then in part D, just calculate the buoyant force based on the volume of this object. And so when I say displaced, volume displaced, the interpretation of that is that this plastic cube that's in the water, it pushes the liquid that's surrounding it out of the way. And so it's displacing some water. That's what I mean by the volume displaced, is whatever this is taking up the space that normally would be occupied by the liquid. So let me bring up the lights, go through steps A through D, and see if we get the same force with either approach. All right, let's take a quick look at the solution here. So in step A, we're trying to find the force that's acting on the bottom. So it's pushing straight up from underneath the water. So we can find the pressure at that depth by multiplying the depth of 4 meters by the unit weight, and then the area that the pressure is acting over. It's distributed over an area of 1 square meter. So that's how we can get the 39240 newtons, and it's pushing up. And then the force from above that's pushing down is going to be equal to the depth of 3 meters by the unit weight of 9810, and then that's multiplied by 1 square meter. So the downward force is 29430 newtons, and so that's pushing down. So the net difference, if you've got one force pushing up and one force pushing down, and the force pushing up is larger, then we should have a positive difference. And the difference here is, 9810 newtons upward. So that means there's going to be a tendency for this to float up. Since we know the weight is negligible, it's not in equilibrium. This is going to be rising to the surface. Now if we look at the other method, just considering the buoyant force, we should get the same value for the upward force. If we just look at the volume of water that's displaced by this object, it's 1 cubic meter times the unit weight, so 9810 newtons upward. Yes? Yeah, because the object is what's displacing water. And so we multiply it by the unit weight of the fluid that's being displaced, which is water, and the volume that's being displaced by the object. And so, yeah, we talk about the volume of the object itself.
It's going to go up.
This one is going to go up. Yeah, it's not in equilibrium. Now, let's mention a couple of things. So right now, we said it's going to be moving up. Right now, the top is at a depth of 3 meters. What about when it moves up through the water a little bit? Let's see when it's at a depth of only 2 meters instead of 3. Are the buoyant forces going to change? The difference will stay the same. And so think about it. The pressures are going to be different. The pressure acting on the bottom will be lower, but the pressure acting on the top will also be lower. And so as it rises through the fluid, although the pressures are changing, the net difference between them is the same. So the buoyant forces are not dependent on the depth. And we usually think that when you're really deep in the water, there's a ton of pressure, it's pushing so hard on the object, and that's true. But the buoyant force, if we go to our simplified formula, nowhere in the buoyant force formula here does it say what is the depth. It simply depends on the unit weight and the volume of water displaced. Okay, are there any other questions before we move away from this example? Now consider this object. It's only partly submerged. And so sometimes the volume of the object and the volume of water that object displaces is not the same thing. So here you can see that the overall volume of the object would include A, B, C, D, where they're just sort of marking some of the key points of that object. But V sub D is the submerged volume. The V sub D, remember, D stands for displaced, the amount of water that's displaced there. So here the buoyant force that's acting upward is going to be the unit weight times V sub D. Now, just by looking at it, we can tell that whatever this is does not have negligible weight. In that previous example, we said that the plastic cube has negligible weight, and so it was not in equilibrium, it was floating up. Assuming that this is in equilibrium, what that means is that there's enough weight acting downward so that this much of the object is submerged. We're going to take a look at that partially submerged case with this block. And so we have a block that's underwater, and it's again made of plastic. We don't know what kind of plastic. We don't know really anything about the plastic yet, except for right now it is in equilibrium. It's floating in equilibrium. And so although it's 5 meters tall, it's submerged at a depth of 4.6 meters. So we're going to go through these numbered steps 1 through 5. I'd like you to go through them, and then later on I'll show you the solution. But the point of this illustration is to show you that we can learn a little bit about what kind of plastic this is by how it floats. At the end, you're going to calculate the specific gravity of the block. And by specific gravity, I mean S is where it's the unit weight of the block divided by the unit weight of water. That kind of specific gravity. And usually specific gravity is a property we apply to fluids, but you can apply that property to solids as well. And then what I mean by, in part 4, the specific weight of the block, I mean you can calculate the gamma of the block as being the weight of the block divided by the volume of the block. Okay, so I think step 1, 2, and 3 are going to be very, well, easy, maybe isn't the right word, but you'll be able to find them pretty directly. But then with these hints, I think you've got the formulas you need for parts 4 and 5. All right, so in part one, we find that we need to find the buoyant force. And the key to calculating the buoyant force is just to find the weight of the water that's been pushed out of the way by this block. So its submerged volume is 4.6 by 10 by 10. And if you multiply that by the unit weight of the liquid, then it's 4,510,000 newtons. Now, one thing I'll remind you is it's so important to always write the units next to every number. It's an investment in seeing your mistakes. Because if you always write these units next to your numbers, you're going to catch yourself if, for example, you use 9.81 instead of 9810. If you write, 9.81 would be kilonewtons, then you're going to remind yourself so that you could write the final answer in the correct units. And so it needs to be the right numbers and the right units for the full credit on a quiz or an exam. All right, now let me go back to the problem statement and ask you a question. I told you that this was in equilibrium, but what clue do we have from the problem statement that this is in equilibrium? Here in the description, there's the way it's written here, it tells you that it's in equilibrium. Any guess? It floats. It floats in the water as shown. And so it's not just that it floats, but it floats, and because if it floated, maybe it's only part of the way coming up out of the water here. But floats as shown says that it's floating, and how you see is its sort of final resting place when it finally stops coming up out of the water and is in equilibrium. So sometimes you have to pay attention to the minutia of the language to know that yes, this is in equilibrium. And so now that we know it's in equilibrium, that's where it's from the way that it's floating that means it's in equilibrium. And so the weight, which is acting down, and the buoyant force, which is pushing up, are in equilibrium. And so we don't have to do any calculations to find the weight of the object. We just know that it's equal to whatever the buoyant force was. Volume of the block. It's talking about the physical volume of the block, not just the submerged volume. And the reason why is that we're going to use this volume when we calculate the specific weight of the block. And so that's step 4, is where we're finding the specific weight of the block with the formula that you can find a unit weight of something, whether it's a liquid or a solid. So in this case, the unit weight is for a solid object, and it's just the definition of that is the weight of the object divided by the volume of the object. And we know that the reason why it's floating is that its unit weight is less than the unit weight of water. If this was a dense object where the density is greater than 1,000 kilograms per cubic meter, or if the unit weight is greater than 9810, it would sink. But here, the unit weight is less than that, and that's why it's floating, is because its unit weight is less than the unit weight of water. And so we can calculate the specific gravity, 0.92, and it's not a coincidence that the block is 92% submerged. 0.92, or expressed as a percentage, the specific gravity is 92% that of water. If you look at the dimensions, the depth, it was 4.6 meters of its 5-meter height submerged. And so that gives us an idea that you can determine the specific gravity of some object by looking at how it floats in the water. The percent submergence and specific gravity are the same thing. All right, so are there questions from this example, either the concepts or the calculations?
Professor, usually when we solve a question about pressure, we apply the pressure is equal to delta H times the delta H times area.
Okay, so you're saying, like, could we have found the buoyant force by looking at the depth and the area?
No, I mean, like, don't we have like pressure acting other than the buoyancy?
Well, there's pressure acting on the side. Is that what you mean?
And on the bottom, there's no.
On the bottom? This is the pressure that's acting on the bottom.
It's only the buoyancy.
Yep. So the buoyant force, another way we could find that buoyant force is what's the bottom surface area? It's 10 by 10, right? So 10 by 10, so that's 100 meters squared is the bottom surface area. And then the pressure at that depth is going to be delta H times gamma. So the delta H is 4.6 meters. and then the gamma is 9810 newtons per meter cubed. So you could find that pressure and multiply it by the area, and you're going to get this same force. Yeah, exactly. And then the pressures on the side, it is a box, and so there's a pressure acting on the front, on the back, and both sides, and all of those forces are canceling each other out, so it's not moving around because of any of the side forces. Yes?
So not given the width and the 10 and 10.
Yeah.
Can we start from the bottom of this process and then solve it backwards? And then we divide 5 by, divide 4.6 by 5, we find the percentage is submerged.
Mm-hmm.
And then work.
Well, that would tell you it would tell you the unit weight, and it would tell you the specific gravity. But I don't know that eventually we'd be able to know the dimensions of it. But you wouldn't. I mean, there's lots of information you can get without knowing the dimensions. So it depends on what the problem is asking. And we're going to do one in just a minute where you're not given the dimensions. And so maybe that'll address the point you're bringing up, that you don't always need to know the dimensions. Yeah. All right. So this is the one I'm talking about. In this case, we've got two objects that are connected to each other with a cable, like a thin wire cable. We know some things about the one on top. The block on top is made out of wood, and it's mostly submerged. And then the object in the bottom is made out of metal. So the given information is that the block on top is 10 millimeters by 50 millimeters by 50 millimeters, and we know the specific gravity of it. And then the metal object, we know only the volume. We don't know the weight of it yet. We don't know the density of it, only just the volume. And so what we want to do is find the tension in the cable and then the mass of object 2. Now I'm going to, rather than having you do all the calculations on this, I'm going to have you do some of the calculations and then we'll go through the rest of it together. So the first step here is find the buoyant forces on object 1 and object 2, and then also do step B, where you're finding the weight of object 1 based on the specific gravity, which is given, and the volume of it. Okay, so steps A and step B is what I'd like you to do, and then we'll go through the rest of the calculations together. All right, so let's take a look at the solution here. So we've got a floating block connected to a metal piece in the water, and we know its dimensions in terms of millimeters and so on. So, all right. Here is a beginning thing. I did my little drawing, and I took a look at the dimensions. And the volume of object 1 is 6,600 cubic millimeters. And in terms of cubic meters, it's 6.6 times 10 to the minus 6th cubic meters. Okay, so I want to find the buoyant force, the force that the water is pushing on object 1 and 2. And what we already know about buoyant force is it's equal to the volume of water displaced. And so I'm going to calculate the displaced volume of water. It's 7.5 millimeters, and I converted that into meters, multiplied by 50 millimeters by 50 millimeters. And so that's the submerged volume, multiplying it by the unit weight of the water. So 0.184 newtons is the force pushing up on object 1. And object 2 is a little bit easier because we don't have to calculate the volume. It's just given directly. Object 2 is, the volume is 6.6 times 10 to the minus 6. So that was the given volume of object 2. So we've got our buoyant forces. Both of those are pushing up. And we were given the specific gravity of object 1. And we know its volume, the volume of object 1, the full physical volume, not just the submerged volume, but the actual physical volume of that object, similar to the last example we did where there was the submerged volume and then there was the object's physical volume. So here we want to find out the weight of object 1 by first of all calculating the unit weight of that floating wooden block. And so that floating wooden block has a specific gravity of 0.3. If we multiply that by the unit weight of water, which is always what specific gravities are relative to, then we can find the unit weight of the block. Mm-hmm. For this one? I don't think so. No, I think it's as shown, because remember it's 6,600. Yeah. All right. Okay, so we've got, we were at the unit weight of the block, and now the weight of the block is going to be the unit weight multiplied by the volume. Okay, so the full overall volume of the block multiplied by the unit weight. So that tells me the weight that's acting down of object 1. So let's do a force balance on that wooden block, object 1. Okay, so what are the forces? There's the weight that's acting down, there's the buoyant force that's pushing up, and then there's some force in the cable that's pulling it down as well. So those are the three forces that are acting on object 1. And we know that it's in equilibrium, and so the sum of the forces in the vertical direction are equal to 0. So another way of saying that is that the forces up are equal to the forces down. So the force up is the buoyant force. That's the only thing pushing the block upward. And then there's two forces that are down, the weight of the object and the tension in the cable. We know both the buoyant and the weight, but we don't know the tension in the cable yet. That's what we're solving for in the force balance. So we can find the tension in the cable. It's 0.1104 newtons, pulling it down. Okay, so are there questions so far on this one? So now if we do a drawing of the next object, if we do a force balance on this metal part that's fully submerged, what are the forces? There's the weight going down, the buoyant force going up, and the tension in the cable is pulling this one up. So the tension was down for the other object, but it's pulling upward on that one that's fully submerged. So that's how we find the weight, because we already knew the tension, and we previously, in the earlier step, calculated the buoyant force. So now we know the weight of object 2. Any questions with that one? All right. So then we can find the mass of it, because we know the weight and we know the volume. I guess we don't need the volume for this. We just have the weight, and G gives us the mass. So the mass of it is 0.0179 kilograms. All right. So you have a homework problem that's pretty similar to this. What I'd suggest you do is you can really help yourself out by taking a glance at the homework right now and start to connect the ideas from the lecture and connect the ideas from the example to the homework, because next Saturday night you're going to forget most of what we've talked about today, right? It will have been a long weekend. It's the middle of the night Saturday, and you're not going to remember the details of this example as well as you know them now. So get an early start. Speaking of the homework, let's take a look at some of the key ideas from the problems. Okay, so here you have one that's very similar to what we've just been talking about. There's a problem where it says that there is a buoy that's submerged underwater, and you're given the diameter of the buoy. And so they're also telling you the weight of the metal that the buoy is made out of. And they're telling you there's a chain connecting the bottom of the ocean to that buoy, and then they're saying the maximum force that can be in that chain. And so with that, they're defining the maximum tension in the cable. And so what they're trying to find out is how much scrap iron should you put inside the buoy based on everything, all of the parameters that you're given. So what I'd like you to think about is, what is the anchor chain doing the buoy? If that anchor chain wasn't there, it would float to the surface. And so obviously the anchor chain is pulling down on the buoy. And the water is pushing up. And so you can do a force balance on the buoy similar to the drawings that you just saw in my solution, where you take the object and then you draw the tension is down, the weight is down, and the buoyant forces are up. And ultimately, it's trying to find out the only unknown is the total weight. And in this one, there's two different weights. If we draw, here's the buoy. So we said the tension is down and the buoyant force is up. Now there's weight 1 and weight 2. And weight 1 is already given. It's the weight of the buoy. But they're saying how much scrap should you put in there so that the tension in the cable isn't exceeded. So this is an example of a problem that really, you should do this one as quick as possible while all this stuff is still fresh in your mind. All right? And here's another one. And actually, I haven't assigned this problem before to students, and so I was looking at it on Thursday, and I had to scratch my head for a few minutes because it was just unfamiliar. The way that they were presenting the problem, I thought was kind of tricky. And so that's why I picked this one, just to give you some of the key ideas, is because I thought it was kind of a tricky problem. It's not that the underlying fluid mechanics are hard, it's just the way they describe it, the word part of it was a little hard. So here's what I've done. I've done the drawing, and in this problem what they're saying is if you measure a block in water and air, you get different measurements. And probably you've felt that if you go to a swimming pool, how much you weigh if you stand on the scale in the gym, if you took that same scale and you put it in the water, it would probably break the scale. But let's say that the water doesn't damage the scale, and so you get on and it's still working, it would say a different amount because the buoyant forces are pushing up on you in the pool, and so the measured weight would be less. It's not that your weight would actually change, of course. You still have the same mass, you still have the same weight. It's just that the perceived weight would change because what that scale actually measures is the difference between your buoyancy and your weight. And when you're in air, there isn't much buoyancy in air. There's a little bit because you are displacing a fluid. It's just that when you're in air, the fluid you're displacing is gas, which has a really low density, and so there's not much of a buoyant force. But in water, the fluid that you're displacing is water, and so you have more of a buoyant force. So here's how it's broken down. When you have that block on top of the scale in air, then the scale is pushing up on the block. That's really what the scale is measuring. It's, I think the easiest way to think about it is the scale isn't measuring the weight of the object so much as how much it's pushing up on the object. Because what we know is if you move that scale into water, it says 300 newtons. And so the scale isn't telling you how much the object weighs because the object's weight didn't change. What it is telling you is that the scale is pushing up with the force of 300 newtons. And so that's like the main, I think, hint that I wanted to give you is consider how much the scale is pushing up in the air versus the water. And then there's also the buoyant forces that are pushing up. Yeah. So it's the buoyant force that's accountable for the difference. And if you know the buoyant forces, then you'll be able to solve the rest of the problem. So just keep that idea in mind. And you can come back to the video if you need to when you're working on problem 100. But do a little sketch like this. And remember that what the scale tells you isn't the object's weight, but it tells you how much force it's pushing up. All right, it's 8:50. We're out of time. Let's just take one look at these announcements before you go. The next assignment's not due until Sunday, but it'd be a great idea to get started early. And when we meet on Tuesday, I'll tell you a little bit more about the exam. Have a great day.